And this is the most important paper, which somehow is also last. The only one left to do. Okay, this is the paper that you're going to copy, essentially, because it's published by me. It's 1998, so you were born in 98.
Yeah, 98,
so
yeah.
more relevant now, coming into your lifespan. You were 2 years old, perhaps, at the time. Gosh, running around. Probably should have been. I mean, there was me doing research at that time. Unbelievable. So you're going to copy this paper, all right?
Okay.
Now, this paper actually focused on measuring T2. Which is called the spin relaxation. These are awful names. I won't tell you why now, but we can talk about it later. And T1 is known as the spin lattice relaxation. It's awful. They're just awful names. They're very misleading. It's just historic how they've become. That's how they've become known. So you're going to measure not T2 but T1. But effectively, you're going to do exactly this work, but measuring T1. And for the sake of this 4 weeks, you're going to assume that T1 equals T2, so there's no difference.
Okay.
Okay? So just for this 4 weeks, and there are certain limits that's kind of true. Okay.
So whether it says T2 near, we can just say it's T1.
You're going to think of it as T1.
Yeah.
And I'm just going to highlight now. So this is the most important paper.
Okay.
Okay, because this is what you're going to be copying. So for now, what I'm going to say is you are going to be generating data that looks like that. So this is 1 over T2, 1 over T1 as against log molecular weight. You're going to look at different lengths of polymers and you're going to see how the T1 varies from molecular weight. So you're going to generate a graph that looks like that.
Yeah.
Okay. You're then going to analyze that graph using this formula. See that?
Yeah.
You're going to use that. From this, you're going to get something called Na and Tor. They're the two parameters that you will get from that. So analysis of this with that will give you those two parameters. You can read what those two parameters are. Okay. You're then going to plot Na as a function of temperature. I mean, I'll just choose this. We did 4 different things, but it doesn't matter. You're going to do one of them. I don't know which one it is. I'm just giving you. It's probably this one.
Yeah.
Okay. You're then going to look at the Tors, and you're going to plot that. Here it is. That's the Tor that you found as a function of temperature.
Yeah.
Okay. And you're going to fit it to this equation. Got that? And then from that, you'll pull out three parameters: Tor naught, B, and T naught. Got that? Good. If you're really brave and you want to try something a bit more challenging, so that's just fine. So you got that. Yeah, it's just there. You could try that if you're brave. So I'll put a little star next to that. Okay. It explains how to do it somewhere in the text nearby. I can't remember exactly where. It explains how to do it here, and you can copy that idea. Now, all this work was done on a fixed magnetic field strength, a normal benchtop machine which worked at 0.5 Tesla, which corresponds to 20 megahertz. That's the natural Lama or precessional or resonance frequency of the proton nuclei inside this machine. So you're going to do all this, but you're going to have the added benefit that you're going to do it across a whole range of frequencies, because that machine, the fast field cycling, is a magical machine that can do NMR from 10 kilohertz to 10 megahertz. It can do 3 orders of magnitude. That's the 10 kilohertz to 10 megahertz. So you could actually do this 1,000 times over. Okay, you can do all this analysis at 10 kilohertz, and at every single frequency, which is infinite, all the way up to 10 megahertz.
Yeah.
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 There you go. So you'll have not only will you get NA.
Is there any in particular wanted to do, or do we have freedom to do any in the range?
Yeah, I think. Well, that's part of the advanced lab thing, is that you've got to work out sort of what to do and why it might be interesting, I think, which is at this moment a bit opaque, I guess. So you can NA. You can do that as a function of frequency and temperature. Tor as a function of frequency and temperature. Tor naught, B, T naught, ditto. Yeah. So this is I'll put little stars. There you go. That's the key. The second most important one, because it's very similar, is that one, because it's very similar. But this is the one you're actually going to follow. Okay. So the way when it's a 3-week period, I mean this is a 4-week period. So let's think of it in a 4-week sense. But remember, you should only be working at 3/4 rate. That's for you to manage. I can't make you work at 3/4 rate. I don't know what you're doing. So let's think of it this way. The first week is primarily research. Okay.
Read all these papers and stuff.
Yeah, and I'll expand a little bit more on that. But okay.
Yeah.
Week 2 and 3 are essentially experimental, getting lots of data.
Yeah.
And week 4 is essentially analysis. Okay, now that's just a broad kind of categorization, because when you're watching a measurement take place and you're letting the machine scan for an hour, you can still do a bit of research, can't you? You're not stuck at that point. And as soon as you've got some data, you can start to do some analysis, can't you? And when you're doing the analysis, you can still keep on doing some research. It's not like they're mutually exclusive, but just roughly, the focus for week 1 is research, the focus for week 2 and 3 is measurements, and the focus for week 4 is analysis. Yeah? Okay, got that. Now, in terms of the research, what makes good research is asking good questions. So what I want to see is that you ask yourself interesting questions. Now, there's no right or wrong kind of questions. Well, within reason there are. You start asking questions about black holes, then of course that's wrong in the sense that it's off topic. So let me indicate. These are not meant to be for you to write down and then go, I will answer these questions because I might mention them. This is just to be illustrative. Yes.
Yeah.
So you're doing research. So ask yourself an interesting question, like who uses NMR? Who uses fast field cycle NMR? Who uses relaxometry? Why do they use it? What's their research? What's their motivation behind that? What's the latest results on this? Anything like that, So you ask yourself an interesting question, and then you try and answer it. Okay. And you both know about Web of Science?
No.
Web of Science is the most important research tool. In fact, it's my only one I use. Yeah. I know there's things like Google, and I know that. But Web of Science is a database that has this is almost true, virtually every single peer-reviewed publication there's ever been. It's incredible. They've gone back in time, so to speak, and digitized papers, and I think they're right up to date to about 1900, I think. They've got, which is before things were electronic in any kind of shape or form. And so you can search them by keywords, by authors. You can see who cited them, who's used them, everything like that. So Web of Science basically is your gateway to all kind of peer-reviewed things. If you just do Google and you find things, you don't know whether that thing is being peer-reviewed. And that is the difference between science and non-science or nonsense. Simply. Because it's peer review doesn't make something right, doesn't make it safely, definitely right, but it is a kind of good safety net. It's one of the ways to filter out crazy people from non-crazy people, because so many people will tell you things like, oh, well, this thing about life, or this thing about reality is true. Gosh, vaccines, for example, cause autism. What you say to somebody like that as a good filter is, show me the peer-reviewed literature that supports your position.
Yeah.
Oh, you don't have any. Oh no, it's a conspiracy. It's always a conspiracy. Yes, that's your filter. That's that's an alarm bell. There may be conspiracies also. I'm not saying they don't exist, but that's an alarm bell that should go off in your head. Is
Like the Earth's flat.
Yes, and so the layperson always thinks they know more than the expert, and it's just they don't, do they? Because they're not the expert. And the peer review is right. You've got to remember though, on the other side, just to counterbalance that, a publication is different to a textbook. So when somebody writes, or when I write a research paper, it is your best guess given the information. Guess is probably too weak, but it's something like a best guess given what you know at that moment. And so most publications are wrong. And just because it's written down, because it's difficult, it's in print, you read it, it looks official, it's got nice authors, it looks like it's true, but you've got to get in your head that these things are state of the art when they're published. They're meant to be a little bit speculative. They're meant to be, this is consistent with my data. I'm kind of putting this forward as an idea. It's not set in stone yet, you see. So you'll find that papers